There is a lot to cover in the topic of energy, and to be able to get full marks in exam questions, you need to be really precise with your language. So let's start off with the basics. There are some energy stores, ways in which energy can be stored in different situations. Those stores are kinetic, thermal, chemical, gravitational potential, and elastic potential. Yes, you do need to say the potential part for those energy stores. Kinetic energy is contained in anything that moves. Thermal energy is in anything that is hot or has heat energy. So an example for kinetic would be a car. Thermal energy would just be hot water. Chemical energy is contained in batteries and food and fuel. So things like petrol or diesel contain chemical energy. Gravitational potential energy is increased when anything goes up in height, like a plane. And elastic potential is contained in a spring as well as elastic bands. Now, nuclear and magnetic energy stores are two energy stores, but we deal with them separately in different topics. So we're not going to worry about them here. So energy is always conserved. What that means is that in the law of conservation of energy is that it is never created or destroyed in what's called a closed system. That will be your second mark of a 2-mark answer. It cannot be created or destroyed, only transferred. So what is a closed system? Well, a closed system, as the name suggests, means that nothing can get in or out. In particularly here, there's going to be no energy transferred in or out. It's a bit of a hypothetical system because in real life, energy is always transferred in or out, as we'll look at later. So let's look at our first example then. So we're going to talk about a ball being dropped, and I'm going to use these little kind of levels of energy to demonstrate this. So at the start, it has lots of gravitational. That will then decrease, and the kinetic energy of the ball will increase. So what we'd say is that the GPE, or gravitational potential energy, goes down and kinetic energy goes up. If a car was to stop, to use its brakes to stop, then the type of energy it has gets transferred into a different one. So it starts off with kinetic energy being quite high, then that would decrease as it stops because it's stopping moving, its speed's going down, and its thermal energy, in this case in the brakes, will increase instead. So less kinetic, more thermal energy stored, and also into the surroundings. Now, the next thing we're going to look at in this topic is all to do with essentially where that energy goes. So that energy, we say, is a really good phrase to learn, is dissipated into the surroundings or into the air as thermal energy. So we could add another little energy store in here, as well as it being going to kinetic as the ball drops. We could also say a bit of it gets lost as thermal energy due to drag. Now, a really good phrase to use here is the reason for that is because work is done against frictional forces like drag and friction itself. Now, how does energy get transferred from one store to another? Well, it's due to these energy transfers. So just like a football transfer, how does one player get from a club to another? It's by making a transfer. So the energy can be transferred as either force or heating, electric current or waves, for example, light or sound waves. So let's talk about, for example, a catapult. Catapult being one of those things you pull back elastic band and let go a ball. So the example here would be the energy being transferred from elastic potential energy when you pull it back to kinetic energy as you let it go. Now, the thing that is responsible for giving it kinetic energy is the force that is kind of from the elastic band on the ball. So that will be the energy transferred. For our car example earlier, it gets hotter due to heating, which I know sounds an obvious thing to say, but that will be the energy transfer responsible for that particular example. Okay, next we're going to talk about then, well, go back to our example of a car. Instead of stopping, let's talk about our car moving in the first place. So what do you put into a car to get it to move? You put chemical energy in, and the whole point via the fuel, and the whole point is for the car to move, so it has kinetic energy. Now, as well as that, if you've ever felt the bonnet of a car, the car will be getting hot even if it's not braking. So what we'd say then is that the kinetic energy here is useful, but that thermal energy is wasted. So the more useful energy and the less wasted energy a device or an appliance or anything does, then you have what's called a higher efficiency. Now, efficiency, that's the definition of it. So it means high efficiency means more useful, less wasted energy. But there's a calculation for it too. So let's say in this example, I put 200 joules in. I get 80 joules of kinetic and 120 joules of thermal energy. To calculate the efficiency, I divide the useful energy out divided by the total energy in. So in this example, I've got 80 joules out, I put 200 in, so overall that equals 0.4, or as a percentage, that would equal 40% if you times by 100 to make it a percentage. Now, efficiency can never be bigger than 1, because that would mean you're getting more energy out than you're putting in, which we know cannot happen. If I wanted to improve the efficiency of, say, a car or any device, there are a couple of things I can do. I can lubricate the engine, I can streamline or make it more aerodynamically shaped, or not in a car but in other situations I can use low resistance wires in electrical appliances. Now, lubrication, for example engine oil, reduces the energy lost or the work done due to friction in the engine. Engine's got lots of moving parts, so you reduce the energy lost there as heat. If you want to streamline it, it's a similar kind of idea. You reduce the energy lost or work done due to drag. You're trying to reduce drag and reduce the thermal energy into the surroundings. Low resistance wires would be used, and you might want to look back at my video about electricity to reduce friction between electrons and ions in wires themselves. Now, I've used work done quite a lot there as a phrase. It's really important to note it's exactly the same thing as saying energy transferred. So I can say energy transferred or work done in exactly the same scenarios. They mean the same thing. Now, there is also an equation to calculate this thing called work done, which is the force multiplied by distance. So it's got the same units in joules, and force is in newtons, distance we always put in meters. There are also a couple of other equations in this topic we're going to look at. So kinetic energy equals a half times by mass times by speed squared. You should know the units for those. I put in red now. Don't forget to square the speed. GPE, or gravitational potential energy, is mass times by G times by a change in height. Now, G here is gravitational field strength, which is a bit of a mouthful to say, so we just write down G. On planet Earth, they'll tell you in a question, it is 9.8, but it'll be different on different planets. The heavier the planet, the higher the gravitational field strength. So I'm not going to do any practice questions here. I will do some in the future about those formulae, but you need to make sure you know how to use them using something like FIFA to get your maximum marks. There's one more, which is elastic potential energy, which is equal to a half times by something called the spring constant of the spring you're talking about, times by the extension squared. Again, extension has to be in meters. Okay, now we're not going to do the full calculations here, but I'm going to show you a couple of really common examples that come up, and these are like the kind of really grade 8, grade 9 level questions. So a question might ask you for a roller coaster, for example, to find the speed at the bottom of a slope, and they might give you the height of the slope, and they might give you the mass of the roller coaster cart. So what you need to know is that you can work out the gravitational potential energy at the start and make sure you know the kinetic energy is 0 because it's not moving, and the kinetic energy at the end would be exactly the same as the gravitational potential energy at the top. So therefore that allows you to find the speed. You could also have an example with like a catapult where you might have to work out the elastic potential energy and then use that to work out the speed. So you could work out elastic potential energy and then use that, say it's equal to half times by mass times by speed squared. Now sometimes they'll work that through in a question, sometimes you'll be expected to know how to do it. Now this all assumes that energy is not lost due to friction, because if it is, then these two things are not equal to each other. So you won't get the maximum speed that you'd be able to calculate. Okay, now power is essentially an equation. So there's a definition for it, but the equation we're given to you is energy or work done divided by time. It's measured in watts or capital W, and it is the rate of energy transferred. Really good word to use, that rate. Rate just means something divided by time or per second. Now to be able to use this, I mean, it really comes up a lot in paper 1. You could be asked to substitute it in instead of energy in the specific heat capacity equation or in the kinetic energy equation, so just be aware that's one of the sneakiest things you could get in a multi-step equation is power times time instead of energy. Now, because power is so closely related to energy, we can also use it to define efficiency as useful power out divided by total power in. Well done, you got through to the end of the energy topic.